transformer models rely on positional embeddings to help them uphold the sequential nature of the data when they process it. The original transformer model introduced sinusoidal positional embeddings, where each hidden dimension is modeled via a sinusoidal curve. Since then, different solutions have come and gone. In this modern era of LLMs, most models have found one type of embeddings to be performant and generalizable, that is, RoPE embeddings. RoPE stands for Rotary Positional Embeddings, and as the name suggests, its primary functionality is rotating query and key vectors based on their position in the sequence. As we go through the video, we will see why this is important and things will fall into place. So, with no pun intended, let's get the wheel spinning. The flagship computation of a transformer model is the self-attention layer computation, which revolves around three ingredients: queries, keys, and values. Out of these, queries and keys are used to compute the attention metrics. If you'd like to learn about the end-to-end computation in transformer models, check out my video on the transformer model. Each position has a query and a key. In our case, let's assume a dimensionality of 2. So each query or key is a 2D vector. When computing the attention metrics, we want it to encode two characteristics. Tokens that have similar token embeddings should have a higher score, which is a no-brainer. For example, if the two tokens are cat and dog, it makes sense to give them a higher score as they appear in very similar contexts. Next, the score should be higher for words that are close together. Again, quite sensible. The further apart two words are, the less likely for them to be related. You can see the effect of this positional behavior from the bottom attention metrics, where the intensity is highest along the diagonal. The diagonal is where the query and the key share the same position, and the score declines as you go in the orthogonal direction to the diagonal. Each entry in this attention matrix is the dot product of some qm and kn. Since we are working with 2D vectors, we can visualize the query and the key on a 2D plane. Let's then switch to the polar coordinates. Now, here's one way to think about the relationships between the q and k vectors and the two versions of the attention matrix that needs to be captured. The magnitude or the radial component of the vector contributes to the token similarity matrix. That is, the similarity between radial components denoted by norm of q dot norm of k corresponds to the token embedding similarity at m, n position. The angles of q and k, theta m and theta n, contributes to the positional similarity at m, n position. Here's something important about this design. The angle component only depends on the position of the vector in the sequence and is independent of the actual token embeddings. On the other hand, the token similarity is captured by the radial component of the vector and is independent of the angle it creates. Remember this, as this school of thought lays the intuition for RoPE embeddings. Next, we will discuss how we can design functions to capture these properties during the attention computation. We are not so much worried about the token similarity as we are about the positional similarity. So, for the rest of this talk, we will assume same token everywhere. So the token similarity attention matrix has the same value everywhere. Now the only differentiator is how we design the positional embeddings. Before we dive headfirst to the RoPE computation, let's motivate ourselves by learning what's wrong with the sinusoidal embeddings. Here's what the sinusoidal embeddings look like for 2D query key vectors. All we do is push these dots along the curves and take measurements at each position. So at position 0, it's 0, 1, and position 1, it's 0.88, 0.61, and so on. If you compute the actual values at m equals 1, 2, 3, and so on, you will get just slightly different results due to precision issues in our computation. This looks like a sensible thing for a positional embedding. The values seem to gracefully go up and down based on their position. So what's the issue? Once the position embeddings are computed, they are added to X. So let's see how this affects an example vector. For simplicity, let's pick 1, 1. Here's what's wrong. Though conceptually it looks good, not so much in practice. The vector seems to move a bit chaotically as the position changes. It's difficult to see a pattern in the way it moves. Both the magnitude and the angle changes significantly from each positional shift. Also remember, this is only 2 dimensions. Standard transformer models have hundreds of them, and things are probably getting unimaginably complex when you scale up to those numbers. Here's a more conversational view of what might be happening in this model. First, you give the model some data. The dog appears at position 4, bark at 6, and purr at 20. Then the model asks, what are these positions? Then you tell the model that designed using specialized sinusoidals to provide a vector at each position. But all that the model sees is a table of numbers. As we saw, it's hard to see the pattern through those numbers. The model does the best it can given the situation. It's going to memorize these positions and learn in the pattern. Here's an analogy. Imagine you have an exam coming up and you haven't studied for. So the night before the exam, you hit the books and try to study the material. But concepts are tough to learn and you're running out of time. So what do? You try to memorize the answers instead. The transformer model opts into something similar. But unlike you, the transformer model has its reasons to memorize answers. First reason, these models have billions of parameters, and as you know, the more parameters, the more overfitting or memorization takes place. Second reason, when being trained on trillions of tokens, it probably sees most of the words at all possible positions in the sequence. So there's hardly any reason for the model to go above and beyond to learn patterns. Continuing on our conversation, you train the model this way using 20 positions, and then at the inference time, you ask about position 21. This will confuse the model so much because it has no notion of a position 21. The model asks, what is position 21? And outputs something erratic. Research has already confirmed this behavior. The perplexity of the models trained using sinusoidals explored past the training length. Now let's learn how RoPE fixes this. RoPE is built on a simple concept. Instead of trying to mash the token and position embeddings into a paste by adding the two together and computing Q, let's find a transformation for Q and its position M that gives a new vector. The idea they came up with is rotating Q by a factor of m theta, where theta is a constant. It depends on the index of the hidden dimension d. Since we only have d equals 2, theta will be 1. If you had a hidden dimensionality greater than 2, you'd have several thetas, causing each pair of dimensions to rotate at different speeds. We'll chat about d greater than 2 case later. That's what all these equations on the left do, rotating q by m theta. The uppercase R denotes the standard rotation matrix. When you multiply a matrix or a vector by this, you're simply rotating that matrix or vector by some angle. Here's what you get for different positions of Q when you use this equation. You can already see how well behaved Q is with this new embedding. Q rotates around counterclockwise by some theta every time you shift the position to the right. But one question still remains. How does it scale to d greater than 2? Since we have an R that can only rotate a vector on a 2D plane. For this, they use a trick. They break Q or K into blocks of 2. So for d equals 4, we have 2 blocks, and more generally, for a d-dimensional matrix, you'd have d divided by 2 blocks. Then we can repeat the same operations we did for d equals 2 for each block independently. Specifically, we convert R to a block diagonal rotation matrix. Each block is associated with one block of Q or K. Each rotation block will have its own theta constant, and theta depends on the index along the hidden dimension. Multiplying a d-dimensional vector by a block diagonal R means each block in Q or K will be rotated by the angle unique to that block in R. To see how this works, we will break our 4-dimensional vector to two 2D vectors and see how the rotation changes. You can see that the new vector in green moves ever so slightly every time the yellow vector makes a big jump. Now you have the full idea. Each block of Q or K will rotate at different speeds, but they rotate in a consistent, predictable way, always. In combination, it gives the positionally embedded version of Q or K. As you can see in this graph, RoPE embeddings are much more resilient to out-of-time predictions than transformers with the sinusoidal embeddings. They also generally perform better on log likelihood loss. There is also a paper that explains how to increase the context window length of an already trained model using interpolation techniques. But that's a story for another day. Let's also look at how the equations are changing from sinusoidal positional embeddings to RoPE embeddings. First, we're going to ditch the positional embeddings, which leaves us with WQXM transpose dot WKXN. Then we're going to introduce R theta, one for Q and one for K. Then we're going to arrange this in a way that the R thetas are close together. And finally, we arrive at the equation that is in the paper. This brings us to the end of this video. Though the RoPE paper is full of mathematics, conceptually, this is all that happens, rotating Q and K by some angle, which is dependent on their position in the sequence. As he saw, the erratic nature in which sinusoidal positional embeddings move produces models that aren't able to generalize beyond training sequence length. This lays the motivation for RoPE. Due to RoPE behaving in a predictable manner as the position changes, it's able to adapt much better to sequence lengths beyond training length. There's another technique called alibi, which claims to be even more superior than RoPE. But right now, RoPE is the most commoditized positional embedding for LLMs. If you enjoyed this video and like to see more videos about machine learning and large language models, subscribe to my channel, Deep Learning Hero. I will see you soon with another video.